evening, everyone. I am Pinrayda Hassan. The topic that I'm going to present tonight is all about coagulation, instrumentation, and technology advancements. Coagulometers. What are coagulometer and its uses? A blood coagulometer is an analyzer used to test the coagulation efficiency of blood so as to diagnose and assess bleeding disorders such as hemophilia, or to monitor patients who are taking anticoagulant medicines such as aspirin, heparin, or warfarin. How do you use a coagulometer? The central microchannel is designed to suck the blood in as soon as the drop touches the center of the plate. Approach your finger gently and carefully towards the plate to apply your blood drop onto it. It is important not to press your finger on the plate and to apply the blood drop in one single action. Coagulometers has three types: the manual, semi-automated, or automated. Manual and semi-automated coagulometers. This requires the operator to deliver test plasma and reagents manually to the action cuvettes and limit testing to one or two specimens at a time. Requires considerable operator time and expertise. These are relatively inexpensive instruments, and they are useful for low-volume clinical laboratories and for research laboratories. So in this drawing, I have these manual coagulometers from IndiaMart factory and BioBase factory, as well as the semi-automated coagulometer, the Ares semi-automatic coagulometer, and Coax semi-automated coagulometers. Automated coagulometers are expensive and laboratory staff requires specialized training to operate and maintain them. Example, the Helena AC4 is a fast, flexible, accurate photo-optical, fully automated coagulometer suitable for clotting, chromogenic, and immunoturbidimetric measuring. One-channel semi-automated coagulometer which performs measurements of all clotting assays as well as D-dimer. It is ideal for small laboratories. So in this table, it has been summarized the three types of coagulometers, which are the manual, semi-automated, as well as the automated, with its own descriptions and examples. So these are the levels of coagulation instrument automations. Manual. All reagents and specimens are transferred manually by the operator. Temperature is maintained by a water bath or heat block. External measurement by operator may be required. Endpoint is determined visually by the operator. Timer is initiated and stopped by the operator. Example, tilt tube, wire loop. For the semi-automated, all reagents and specimens are transferred manually by the operator, same as the manual operator. But the only difference, this instrument usually contains a device for maintaining constant 37 degrees centigrade temperature. Analyzer may internally monitor temperature. Instruments has a mechanism to initiate a timing device automatically on addition of final reagent, and mechanism is detecting clot formation and stopping the timer. Unlike the manual, it has been operated by the operator. And this instrument has its own internal monitor temperature. Example, vibrometer, start 4, cascade M and M4, BFT2, KC1, and KC4. Automated. All reagents automatically by the instrument. Specimens may or may not be automatically pipetted. Analyzer contains monitoring devices and an internal mechanism to maintain the monitor constant 37 degrees centigrade temperature throughout the testing sequence. These are initiated and a clot formation is detected automatically. Example, ACL top, star evolutions, star compact and compact CT, Sysmex CA series, BCS XP, and CoaLab. Many technical advances have greatly improved specimen, reagent, and data management, improved test performance, and increased throughput as will be detailed below. Improved accuracy and precision. With the advent of fully automated instruments, precision improved to the extent that duplicate testing is no longer necessary, halving material and reagent costs. Assays are performed with confidence as coefficients of variation of less than 5% are typically achieved and even less than 1% for some tests. Random access testing. Automated coagulometers provide random access testing. For current automated analyzers, the ability to run multiple tests is limited only by the number of reagents that can be stored in the analyzer and the instrument's ability to simultaneously interweave tests that require different endpoint detection methodologies, clot-based, chromogenic, and/or immunogenic. Random access benefits includes improved turnaround time, reduced errors, and reduced labor costs. Improved reagent handling. Reduce reagent and specimen volumes. Current analyzers can perform the same test using 1/2 or even 1/4 of the traditional volumes of reagents and patient specimens. This promotes the use of smaller volumes, especially from the pediatric patients or those from whom specimens are difficult to draw, thus further reducing agent costs. Open reagent system. Recognizing that the ability to select reagents independently of the analyzer is a high priority. Instrument manufacturers have responded by developing systems that provide optimal performance with a variety of coagulation test reagents are compatible with the instrument's methodology. Reagent tracking. Reagent barcoding supports record keeping by tracking reagent properties and enabling the operator to load reagents onto the coagulometer without stopping specimen analysis. Improve specimen management. Primary tube sampling. Instruments often accommodate multiple tube sizes. Significant time savings occurs as a result of elimination of the extra specimen preparation steps and errors resulting from mislabeling of the adequate tube are reduced. Closed tube sampling. Closed tube sampling specimens has improved the safety and efficiency of coagulation testing. Saves staff time. It is also reduces the risk of the staff of specimens exposure through aerosols or spillage and promotes plasma pH stabilization. Automatic dilutions. These conditions can automatically program into the individual test setups on the analyzer. Expanded computer capabilities. Bidirectional interfaces improve efficiency through the ability of the instrument to send specimen barcode information to the laboratory information systems and receive a response listing the test ordered. This eliminates the need for the operator to program each specimen and test. So here are some of the quality features of automated assay performance. Plugging. Improved plugging capabilities alert the operator when preset criteria have been exceeded for instruments, performance, and specimen quality. So this table shows some types of warning flags available on coagulometers. Instrument malfunction flags includes temperature error, photo-optics error, mechanical movement error, probe not aspirating. And for the sample quality flags includes lipemia, hemolysis, icterus, abnormal clot formation, and no endpoint detected. Reflex testing. Reflex testing is the automatic ordering of the test on preset parameters or the results of prior tests. Instruments may be additional dilutions if the initial result is outside the linearity limits, or supplementary tests can be run automatically if clinically indicated by the initial test results. Kinetic of clot formation. Graphing of the kinetics of clot formation is provided on some analyzers such as the ACL-TOP from Instrumentation Laboratory. The graph is generated by an algorithm used to convert multiple raw optical measurements collected over the course of the assay into a final result. In addition to determine the time to clot, this instrument smooths the raw data into a visible curve and uses the curve to check for clot formation integrity. So in this drawing, it is shown that the clot signature from ACL-TOP coagulation analyzers. As the fibrinogen in the plasma specimen converts to fibrin and a solid clot, the change in light transmission through the specimen is recorded. The clot curve consists of baseline, acceleration phase, deceleration phase, and endpoint. The baseline is recorded before clotting occurs. Acceleration reflects clotting and is normally steep because clotting is rapid. The deceleration phase represents the decreasing rate of clot formation as all available fibrinogen converts to fibrin. The endpoint is flat and stable, reflecting consumption of all fibrinogen. A key component is evaluating the clot curve is the y-axis observance, which provides the time interval at a defined minimum that identifies that the clot has developed. Observance suggests to compensate the baseline fibrinogen and the interferences such as leukemia and icterus. So these images is courtesy of Beckman Coulter, Bria, CA. Specimen quality set points. Specimen quality flags such as following are included on some coagulation instrumentations, namely clotted, lipemia, hemolysis, and abnormal clot formation. So for the clotted, will cause falsely shortened clotting times because of premature activation of coagulation factors and platelets that generates factor 7A and thrombin. For the lipemia, it may cause falsely prolonged clotting times on OD sensing instruments because of interference with light transmittance. Hemolysis may cause falsely shortened clotting times because of premature activation of coagulation factors and platelets that generate and thrombin. Icterus bilirubinemia indicates liver dysfunction that may lead to prolonged clotting time because of inadequate clotting factor production, also may interfere with OD sensing instrument. Abnormal clot formation may lead to falsely elevated clotting times because of instrument inability to detect an endpoint. So lastly but not the least, no endpoint detected indicates that the instrument was unable to detect clot formation. The specimen may need to be tested using alternative type of instrument. So that's all, folks. Thank you very much. Thank you, everyone.